In the third and the last part for kinetics, we're going to talk about rates of reactions still, but now we'll talk about how it changes with temperature, okay, and a little bit about mechanisms of reactions. So let's look at the rate of reaction and its dependence on the temperature. Usually what's going to happen is that if you have a higher temperature, then the reaction will go faster. To understand how they go faster at higher temperature, we have to talk about what is called the collision theory. And the collision theory kind of explains how the mechanism also of the reaction works. So what the collision theory states is that molecules have to undergo collisions in order to react. If they don't collide, then the reaction is not taking place. So then there are two things that's going to affect this collision. Number one is going to be the concentration. So if you have more concentration of the reactants, then they're colliding more. And number two, if you have more energy given to the molecules, then they will collide more because now they have more energy. So that's collision theory, okay? So which means that the collisions produce products, which seems reasonable enough. And then there are two parts, okay, for the collision theory also. The first one is orientation of molecules. So not only do the molecules have to collide, but they also have to collide in the correct orientation. If they're not in the right orientation, then they are not going to form the product. So for example, if we look at this collision over here where you have a reactant nitrogen monoxide reacting with chlorine, and the nitrogen has to form a product with chlorine, then nitrogen should be facing chlorine, okay, to form the bond. If the oxygen is facing chlorine, then you're not going to form any bond, which means that no product is forming here. However, when the nitrogen is facing the chlorine, then the product is going to form. Now, if you have plenty and plenty of reactants, then you will have majority of the molecules in the correct orientation. So reactions do happen, and then some reactions work slow, and this could be one of the reasons why it's actually working slow. The second part about the collision theory that's an important part is the activation energy. And the activation energy is the minimum amount of energy required to break bonds, okay, or to get to a particular point, which we will see in the next slide. Another aspect of the collision theory is what we call the transition state theory. In the transition state theory, we say that, okay, collisions are happening, which is great and fine. And once you have the correct collision, then it's going to form an unstable intermediate. Okay, and so in this case, what we do is we end up graphing our progress of reaction. So here is the progress of reaction, and here is the amount of energy on this scale. And so what we see here is the reactants are over here. The reactants will absorb energy and get to a point where the collisions have occurred to form the right orientation. And this is the transition state. If you look at this little symbol over here, that symbol represents transition state. And then eventually that transition state is going to be unstable, which it is unstable. You can't isolate transition states. And then eventually it's going to go ahead and give the products. Okay, and now if you look at this reaction over here, it's almost the same thing where you have the reactants here, and then it absorbs the energy in order to form the intermediate. But if you look here, the final product here, C and D, is different energy state than this product over here. The energy state of this product here is much higher than the reactants. Here, the energy of the products is lower than the reactants. What this indicates is that the energy has been absorbed by the products. If energy has been absorbed by the product, it's called endothermic reaction. And then if energy is less, it means at some point it released this amount of energy, and then it would be an exothermic reaction. So this graph on the top is for endothermic reaction, and the one at the bottom here is for an exothermic reaction. And it's very easy to determine which one is which because of the products, okay, and where they are. So let me show you a few things over here in this graph that are important. First of all, you have your reactants, you have your product, and you have the intermediate, or what we also call the transition state. Okay, so both graphs will have the same thing. The other thing that we mentioned in the previous slide was the activation energy, and I've put that over here again is because it's the minimum amount of energy required to form the transition state, and it's a very important aspect of this graph because it helps us to figure out how much energy is required in order for it to form the transition state. Because if that amount of energy is not there, you will not form the transition state, which means you will not even have the right collisions going on there. So this arrow here, the purple one, shows you what the activation energy is. This one does too, okay, but I made it in purple so that it will be a little bit more clear for you. But this EA, okay, activation energy, energy of activation, this is what is required in order for the reactants to form the transition state. So here you can see that the activation energy is a lot, here it is less, and that is just the nature of the graph. It depends on what kind of a reaction you're doing. The activation energy may be less or more. For the reverse, the activation energy is going to be different. So for example, the endothermic reaction, because it's absorbed so much energy, the reverse is a very small amount of energy, which means that at any point this reaction can actually go back. Whereas in this case, where you have an exothermic reaction, the reverse activation energy is a lot, which means that in this case, the products are actually very stable. Okay, so these graphs tell us a lot about the reactions and about the energies involved, the transition states, and of course, the stability of the product. So Arrhenius equation then is what tells us about how the rate of reaction is dependent on temperature. Okay, so what we need here is this equation, which again K is the rate constant, as you know. And then we have this whole thing over here, so which I need to decode for you. And A is the frequency factor, E is the natural log, EA is the activation energy, R is the gas constant, T is temperature in Kelvin. The R constant that we use here, the gas constant, is slightly different than what we were using before in the gas laws. It's not that it is different, it's just that the units are going to be different for us, because now when we talk about activation energy, we're actually talking about energy units, which is joules. Okay, so that's where R value has to be different, because now we have to calculate R in joules and not as we were calculating before. So anyhow, this is what Arrhenius equation is. Arrhenius was a physical chemist and he came up with this equation. And so here we can see that the rate is dependent on temperature, and the K is rate constant, don't forget that. So then what we do in order to use this equation, okay, for graphing purposes, we can take the natural log, okay, of this equation, and the natural log is this, and it opens up this little part over here, and so now it seems a little bit more manageable, okay, for us. So then if you plot the natural log of K versus 1 over T, it should give us a straight line, okay, because that shows that your rate is directly proportional to temperature. The slope of the line will give us this value, which is the activation energy divided by R, and this is of course all coming from this equation, okay, because usually these equations are for graphing purpose, all right? And so then you can find the activation energy, all right? And the nice thing about graphs is that instead of using these equations, you can use the graph then to calculate the EA, okay? You don't have to use these equations to calculate the activation energy. Another way that we use the Arrhenius equation is when we are trying to figure out the rates of reaction at two different temperatures. Okay, so here if you have K1, K2, which is the rate constant at of 1 and 2 at temperature 1 and 2. Okay, so if you're trying to calculate what the rate would be at different temperatures, this is the equation to use. Now, when we started working with kinetics, I mentioned to you that the rate constant that we calculate, the K value, it is for a particular temperature, and this is the reason why, because rates of reactions are dependent on temperature. If you change the temperature, you will change the rate of reaction. The general rule is that if you change the temperature, if you increase the temperature by 10 degrees Celsius, then you will double the rate of reaction. That is the general rule. It may be a little different here and there, okay? But that's the general rule. So now let's do a little calculation using the Arrhenius equation. This is fairly a simple calculation. And here if you have the rate of reaction going on at different temperatures, 400, 450, and 500, and the K is calculated for each of those temperatures, and we are asked to calculate the activation energy. So now we're going to use the second equation because that's the only one that gives us K1, K2, and then of course at different temperatures. So this is what we are calculating for, EA, activation energy. So we take the EA out, which means if you leave it here also, then R goes on the top. Remember, cross multiplication. Okay, so R goes on the top, and then this goes at the bottom over here of all of this. Okay, and so this is what the rearranged equation looks like. And so then EA is this, and R value, this is the R, this is the gas constant, and you can find this in the textbook also. But this is the gas constant, and this is the one with the joules, okay, and Kelvin mole. So this is not the same with liters. And then we have the K1, K2, all right, over here, and the temperature. Pick any two data points. Okay, it doesn't matter which one is it. Hopefully your activation energy may come out to be the same. You can try it on another set of values. So this is what we get. Now remember, this is natural log. Okay, so once you do this calculation, you have to calculate the natural log of this and then divide it by these numbers. So then you get 91 kilojoules per mole. So easy calculation, not too bad. You just have to learn how to rearrange equations. Here is another one. In a series of experiments on the decomposition of dinitrogen pentoxide and 2O5, rate constants were determined at two different temperatures. So at 35, the rate was this. At 45, the rate was this. What is the activation energy? What is the value of the rate constant at 55? So which means we're given 35, 45, and then we are asked to calculate for 55. So first of all, activation energy. The way we did the activation energy is exactly what we did in the previous slides. So here's the equation that we're going to use. Plug in on the values. In this case, we did not rearrange the equation. The equation is written as it is. You can rearrange it also if you want to. It's the same thing, all right? So this is just a little bit different way of doing the calculation. So here you plug in all the values that are given to you. Just make sure that your ones and your twos stay together, okay? So for example, if K1 is going to be 1.4, then make sure your T1 is 35, okay, 35 plus the 273, okay, to give the Kelvin. And you need Kelvin because your R constant is in Kelvin, all right? So make sure you do those conversions before you get started. So in any case, just make sure that your ones and your twos are consistent. That is the only place where you might actually have problem. Otherwise, the equation is very simple. So then you go ahead and do the calculation on the left-hand side of the equation and the right-hand side of the equation, and another one. And finally, here is the answer. This is all math, so I'm not going over it too much. You can just do that in your calculator. But then finally, here is the activation energy, okay, for this. So then now we have to calculate the value of the rate constant at 55. All right, this is the activation energy. We're going to need that for the next part. So here is the data given to us, okay, and then again here is our equation that we're going to use. Now we can use the activation energy that we calculated from the previous part, okay. K2 is what we are calculating for, okay, don't forget now, because K1 is given to us and K1 is 1.4 and this is at 35, so we're trying to figure out how much at 55, okay, for K2. So once you have all your values plugged in, make sure again your ones and twos are in the right place. And then calculation, again, this is just math. There's nothing I have to do in here. So you do the math here in your calculator, come up with this. Now this is the important part because now this is natural log. So you have to take the anti-log of here and anti-log of here. If you take the anti-log here, you just remove the ln, take the anti-log over here, and this is what you get, 11.90. And so then you calculate for K, which is the multiplication of these two. So this is the equation as I said to you, okay, that's we're going to use a little bit more than the first one, okay, which had the A also, okay, in there. We don't use it that much because I will have you doing calculations at different temperatures. Now for the little bit different part of kinetics, and this is about factors that affect the rate of reaction. We already saw that temperature affects the rate of reaction and how it affects, and we can actually do calculations regarding that. But there are some other things also, okay, that affect the rate of reaction. And one is the concentration of the reactants, okay, and we have seen this before in another calculation that we did with the half-life and all that, is the higher the concentration of the reactants, then the faster the initial rate of reaction that you will have. And again, remember, as far as the collision theory goes, it makes perfect sense because the more collisions you will have of reactants, the more product you will get. And remember also that as the reaction progresses, the rate gets slower and slower, and that's because it's very hard to find the reactant molecules to collide. Okay, and so the first factor affecting is the concentration of reactants. The second one here, and this is not in any particular order by the way, the surface area, okay, of a solid reactant or a catalyst. And the surface area is important because again with the collision theory, if you have more surface area available for reaction, then you will have more collisions. Okay, so for example, liquids will react faster than solids because liquids are more mobile, they are more available. Solids have an inner core and the surface. Okay, and so you can only have the surface available at one time, not the inner part of it. Okay, and so liquids are a little bit more available. And then if you do have to use a solid, which sometimes we do, we can't help it. So in case of solids, if you're using a powder, that will actually be a little bit more available than a block would be, okay, or a strip would be, because powder has smaller particles, and if it's smaller, then the surface area is more in there. So if you can, and you want to, change the rate of your reaction using a different kind of reactant, this would be the way to go. Temperature of the reaction, we already talked about this, okay, as far as the number of collisions go. So more energy, more collisions, more product. And then finally, we have a catalyst, okay, and we haven't talked about a catalyst yet. A catalyst is an entity that speeds up the rate of reaction but does not get consumed in the reaction. This is the key part of a catalyst. I mean, what better thing could there be in this world, okay, that will make a reaction go faster but not get consumed. Okay, so it's like the ultimate for speeding up a rate of reaction. And the way it works is by reducing the activation energy. And if you remember the curve, okay, that we had for the graph, so it reduces that energy. So which means that if you need less activation energy, you'll be easily forming the transition state and so on. Okay, and so the catalyst is really a boon as far as reactions are concerned. Finding the right catalyst takes research. Okay, it's not something that you can just go in the lab and start saying, okay, I'm going to use this as a catalyst. No, actually have to work on finding a good catalyst. It takes research, okay, to find which catalyst will work well for which reaction. So a little bit more about catalysts, because these are very interesting things. Okay, so first of all, again, catalysts speed up the rate of reaction without getting consumed. And also they work by decreasing the activation energy. The key thing that I wanted to mention in this slide here, because you already know the first two, is that there are two kinds of catalysts, homogeneous and heterogeneous. A homogeneous catalyst will mix completely with the reactant. So if you have an acid, for example, in an aqueous solution, so acids are usually aqueous anyway. So if you put, say, concentrated sulfuric acid or dilute sulfuric acid in a water reaction, then yeah, okay, that's a homogeneous system because everything is mixing up. And then we also have something called heterogeneous. And a heterogeneous catalyst, they have different phases. Hetero, different, right? So for example, a solid and a gas, okay? And so these two are very common, obviously, and the homogeneous are generally cheaper and easier to work with because they will mix with the system. So you don't have to do anything at all. Sometimes it's harder to work with this because if they are mixed and you want to isolate them back, then it will be different. Then heterogeneous are better if you want to get your catalyst back. Homogeneous are really good if you don't care about getting them back, which is why these are cheaper also in some cases because you don't want to get them back. It's too much work. Heterogeneous, on the other hand, will work great if you have two different phases, and also sometimes your catalyst is a little bit more expensive, okay, and so you want to get that back. So for example, the catalytic converter in your car, which converts all the exhausts into higher oxidized species. So carbon monoxide gets oxidized to carbon dioxide, sulfur dioxide to sulfur trioxide, and that's the purpose of the catalytic converter. And the way it works is that it has palladium or platinum, which is a precious metal, it's a heavy metal, and it's coated with the oxygen, okay, and so then the gases that go out have to go through the catalytic converter before they go to the exhaust system. So that is actually a heterogeneous catalysis, okay, going on, and as you know, your catalytic converter is an expensive part of your car. So that's homogeneous and heterogeneous. The third kind of catalyst, which I will not put into these two categories, are what we call the biological catalyst. And the biological catalysts are enzymes. And enzymes speed up all sorts of reactions in your body. If there were no enzymes, I don't think we would exist. Okay, or we would be slow as slugs, because a lot of the activities that happen in our body happen faster because of enzymes. We get energy from carbohydrates and fats and everything so quickly and so readily because these enzymes speed up all the reactions. Once you eat something, then the excretion happens fast. Okay, so your body is empty again, and so all of this is happening because of enzymes. So enzymes are biological catalysts. The other thing about enzymes is they're very specific for a particular reaction. Not every enzyme is going to work for everything. One thing I would like to mention over here, which I did not mention before, is that catalysts or enzymes, okay, not catalyst, enzymes generally will work as a zero order reaction, okay, which means that you can have more enzyme if you want, but it's not going to speed up your reaction, okay, so enzymes work as a zero order reaction. One of the goals of studying this kinetics and order of reactions and activation energy and all of this thing is to figure out the reaction mechanism. A reaction mechanism is a step-by-step study of what's going on in a reaction. So, you mix two reactants in a flask, and then something happens and reaction happens and you end up getting product. So what happened in that flask? Okay, and so you can actually get a step-by-step process of how this works. Now, this is all theoretical. Some of it can be proven, but a lot of it is theoretical. Okay, but that theoretical is very good because it's based on data like order of reaction, like activation of energy, etc. Okay, so for example, if we have a reaction like this, where you have nitrogen monoxide reacting with oxygen to give nitrogen dioxide. So if I do this reaction and I find out that my order of reaction with respect to oxygen is 0, it means that oxygen is not taking part in the mechanism. The mechanism is involved only by nitrogen monoxide. So that is how the order of reaction will help me determine how my reaction is proceeding. So it's a whole bunch of combination of things, the transition states, okay, and all of that. This will all help us determine the mechanism. And it really helps in the understanding of what's going on in a reaction. So reactions, because they don't occur in a single step, okay. So for example, if we take this reaction, we can break it down into 2 steps. Okay, so it's possible that we have nitrogen monoxide combining with another nitrogen monoxide, because remember, there are 2 molecules of this to give something like dinitrogen dioxide. So once you have a combination of this, this will now react with 1 mole of the oxygen to now give us the nitrogen dioxide. Now, in this case, only one product is formed, so we don't have to worry about other products. But if we had another product, we would have a proposal for that also, how that is formed, okay? And remember, matter is conserved, okay? Equations are balanced, so every atom is accounted for. One way or another, you have to account for everything. So what happens here with the N2O2? The N2O2 you don't see over here, the nitrogen dioxide, you don't see in this final reaction, and you don't see it in there is because it's an intermediate, okay, in the reaction, which means that it occurs in the reaction, gets consumed in the reaction. You never see it as a reactant, you never see it as a product. So that's what an intermediate would be called. And so what happens for a mechanism is once you've written out all the steps, then all the steps must equal out to a balanced equation. Okay, and if you remember your Hess's law, that's kind of what we did in Hess's law. Is you were given several equations, you were supposed to figure out the enthalpy for one equation. So by the time you were done with everything, you had your final equation. That's exactly what we do for mechanism also. So we write all these things step by step. The rate law that we come out with, okay, must be the same as the experimental rate law, which means that by the time we are done writing all our mechanisms, we should be able to use the molecules that affect the rate of reaction by the way of order of reaction. Okay, so which means the molecules affecting the order of reaction, like as I said before, with this is 0 order, so it's not taking part in the mechanism, hypothetically. So that's what we're talking about over here. Okay, so the rate law must be the same as experimental rate law, which means the mechanism should reflect that. Let's look at an example for a reaction mechanism. I try to keep it simple for you as much as possible because sometimes the reaction mechanisms can be a little bit above our heads. Okay, and so this is kind of how I like to keep the mechanism straightforward. So here it is. The decomposition of hydrogen peroxide is written like this, which gives us water and oxygen, may occur in the following two steps, which means these two steps are given to us. Hydrogen peroxide plus the iodide to give us water and the iodide ion, and then so on. The second step is given here. Then the question goes on. Step 1 is the rate determining step, and then the rate law is K1, and then H2O2 and iodide ion over here. So this tells us that hydrogen peroxide is first order and iodide is also first order. And hopefully you're looking at iodide and thinking, oh, but I don't see it in my equation. Well, yeah, that's something we have to talk about then, right? So here's the question. Explain the role of all the species in the mechanism. So first of all, your iodide, okay, and the iodide does not appear in the overall balanced equation. However, it's given in step 1 and it's given in step 2. Let's look at the location of it. Iodide is given as a reactant and then as a product, okay, in step 2. So which means that it must be a catalyst because it's there in the beginning, it's there at the end. Okay, so iodide is a catalyst and it is taking part in the mechanism of the reaction, and that is why it's right here in the rate law. Okay, otherwise it would not be here. Okay, if it was not taking part in the mechanism, it would not be here. So for example, what is not here? The IO minus, right? That is not part of the rate law. So which means that these two species over here, which got cancelled out, by the way, because the IO minus over here in step 1 is a product, and then in the next step it is the reactant, which means it must be the, yes, intermediate. Okay, because it's not there in the final equation, it is not in the rate law, and it's not there once you balance the equation out. The iodide, okay, is part of the rate law, that's why we have to consider it. But IO minus is not part of the rate law, which means it gets cancelled out, which means it is the intermediate. Okay, so that's how we will determine whether something is taking part in the reaction or not. And then finally, there is one thing which is called reaction molecularity. And molecularity has to do with the number of reactant molecules involved in collision. And this has to do a little bit with the order of reaction also. So if your order of reaction is unimolecular, only one molecule then. Okay, so that would be first order. If it's bimolecular, then it's two reactant molecules, and this is usually what happens in case of second order reactions. And then termolecular, where you have three reactant molecules, which is a little bit rare. We haven't really quite talked about that at all. So unimolecular and bimolecular, this is the one that you will encounter a lot. This is first order, this is second order. And then we have something which is called the rate determining step, and that is the slowest step in the mechanism. And why something would be the slowest step in a mechanism is because maybe some bond is breaking, okay? And sometimes breaking of bonds takes a lot of energy and takes some time, okay? And so the slow step is the rate determining step, okay? So when we talked about the initial rate of reaction, that is determined by the rate determining step. Everything happens very fast, okay? So for example, when you have the graph that you're looking at, the slow steps are occurring over here as the graph is going up. By the time you reach to the transition state, from there everything is downhill, which means everything is happening at a faster rate. Okay, so the rate determining step is the slowest step in the mechanism. That pretty much determines how fast your reaction will go. So what I would like you to know from this little portion, the third and the last portion of kinetics, is that you should be able to calculate the activation energy. If I give you a graph with the activation energy thing, you should be able to label all the things for me in there. That graph is an important graph. You will encounter it again. You should be able to calculate the activation energy, and you should be able to calculate K1, K2s at different temperatures, and so on. Okay, so the Arrhenius equation, that's what I'm talking about here. You should also be able to tell me the speed of reaction when you're comparing two reactions. So if I give you something at a lower temperature or at a higher temperature, you should be able to tell me which one would go faster, or if I give you something in liquid solid, again, you get the idea. And then you should understand the mechanism of reactions. The problem that I solve for you here is probably the extent of the problem I will give you. I will never have you write the mechanism out because that's sometimes a little bit tough to do. So at this point, I'll give you the reaction, I'll give you the steps, and then you can tell me what's the catalyst and what is an intermediate and so on. Okay, good.